We're reaching the end of the first chapter of wave mechanics, which is transverse mechanical waves on a string. So let's quickly run through the definition and derivation part of standing or stationary waves, which come from the superposition of oppositely traveling waves. So we saw that the one way of creating this is by superposition of harmonic waves in opposite directions on a string. But these harmonic waves have to have same or identical frequency and amplitude. So we have on a string wave traveling from this side from a source which is of frequency f and amplitude a, and similarly a wave traveling from the other side from a source which is of same frequency and same amplitude. So if y1 is sine omega t minus kx and y2 is sine omega t plus kx plus phi, and let us take phi to be, for example, if we take it as 2n pi, then y2 can also be written as a sine omega t plus kx. So this makes the solving part more convenient, but we'll also see if we generalize phi instead of 2n pi, we take some general value of phi, then also how we can solve it. And ultimately it makes no difference to the geometry of the standing wave. It only changes the locations of the so-called nodes and antinodes. So let's go over that again. So now we want to understand what is happening in this region of the string at any general point x equal to x by the superposition of these two. So their superposition or overlap will result in what is called the standing wave pattern. So in this particular case, because I have taken the phase difference to be 2n pi, when I do this calculation using the sine A plus sine B formula, of course, in this we understand omega is equal to 2 pi f and k is equal to omega by v or 2 pi by lambda, where v is square root of t by v. So all that is understood. Okay. So doing these steps here and all that, we see that we get y as 2a cos kx sine omega t. So we can interpret it this way, that it is a position dependent amplitude into a harmonic function sine omega t. So we can see that medium particles are in SHM, okay, with frequency equal to omega by 2 pi or time period equal to 2 pi by omega, but they have amplitude, which is the term which I've written in brackets, and amplitude equal to this term. So this is where it becomes different from a traveling wave. Okay. As you can see, this is not the equation of a traveling wave. In fact, it is the equation of a standing wave, because as we saw the snapshot picture, we understood that the shape of the wave is not traveling along the string, it is remaining fixed. So it is called a standing or a stationary wave. So what we understand further here is that it is position dependent amplitude. Okay. So just do a quick recap of this concept. You need not write it down because obviously this is done in the last lecture, but just recall this part, then we'll once again discuss about the definition of nodes and anti-nodes in more detail. Okay, so now looking at the standing wave equation, if we plot the snapshot pictures at various different times, okay, Didi. But as I told you, Peter, you have got this in your notes from the previous lecture. Just go through it once, and in case any part is not clear, let me know. I'll explain it again. But you need not note down this part again because. Okay, so this is done now. Okay, good. So in this equation, we write this in the brackets to understand that this is the amplitude part and this is the time varying harmonic part. Okay. So now if we want to understand, so obviously here the time period for the harmonic motion is 2 pi by omega and the wavelength for that part kx is 2 pi by k, like that. Okay. So now supposing we want to understand the snapshot, that is y as a function of x at various different times. So for example, at t equal to 0, you can see it becomes 0 because sine omega t is sine 0, which will become 0. Then secondly, if we look at the snapshot picture at t equal to 1/8 of the time period, you will see that at this point of time, sine omega t will become sine pi by 4. So that will become 1 by root 2. So the snapshot picture at 1/8 the time period will become 2a cos kx into 1 by root 2. So that will become root 2a cos kx. So we'll plot all these graphs in a moment, but let's just write down these values first. Now, if we progress the time to 1/4 of the cycle, so at 1/4 of the cycle, you can see the sine omega t term will become sine pi by 2. So it would have reached its maximum of 1. So y at t equal to 1/4 of the time period will become 2a cos kx. Okay. Then again, we plot the snapshot picture at another 1/8 time later. So that will become 5t by 8. Is it? No, just 1 by 4. So it becomes 3t by 8 by mistake. Okay. So 3t by 8 if we plot it at. So this sine omega t term you will see will become sine 3 pi by 4. That is again 1 by root 2. So at this time, you're back to root 2a cos kx. Okay. So we are going on increasing the time by a factor of 1 by 8, plus 1 by 8, plus 1 by 8, plus 1 by 8. So if we do this series, till we complete one cycle. So next we will see we'll come to t equal to t by 2. So sine omega t now becomes sine pi. That becomes 0. So we are back to that situation where all the medium particles are at the mean position at t by 2. Okay. So just note it down up to here these values, then we'll continue forward. Okay. So I have gone on increasing the time from t equal to 0 by a factor of 1 by time period, 1 by time period till I have reached half the cycle. Okay. In fact, let's continue this here itself. So another plus 1 by 8. I'll do so. I'll reach the time of t equal to 5t by 8. So my sine omega t term will become sine 5 pi by 4. So this time it will be minus 1 by root 2. So the snapshot picture will now be the graph of minus root 2a cos kx. Then again increase by a factor of t by 8. So this will become 6t by 8 or 3t by 4, 3/4 of a time period. So sine omega t will become sine 3 pi by 2. So that is minus 1. So the snapshot picture will become minus 2a cos kx. Yeah, okay. And so 8 times we've increased by 1 by 8 of time period. So we'll complete the cycle with this one. So t is equal to capital T1. Oh no, we'll come to 7t by 8 and the next time. So we've actually increased it 7 times. Going from 1 to 8, we've increased it 7 times. So one more has to be done. So the sine omega t term will now become sine 7 pi by 4. So that will again be minus 1 by root 2. So and finally, on ninth value, after incrementing the time by t by 8 times, we are at one full cycle. So sine omega t is sine 2 pi, so that's back to 0. So once again, all the particles at one complete cycle are back to their mean position. Okay, so just write down this sequence of values for the snapshot picture equation at various different times, and next we'll plot it. So from that you'll understand how in increments of 1/8 of the cyclic time period, in one complete cycle, how the shape of the string changes. Yeah, Ansh has scroll up. Let's just finish with this section. So we are basically just looking at a review of the concept of standing waves, which comes from the superposition of two such waves. So we'll just give a couple of minutes to Ansh to catch up with this section. This is what we discussed in the last lecture towards the end. The superposition of waves traveling in opposite direction of same frequency and amplitude, creating standing wave patterns. So now we want to understand the snapshot pictures and the geometry of these standing waves in a little more detail today, before we move on to the next section. Okay, good. Okay, so what we did next is we looked at this equation of the standing wave and we substituted the value of time in the sine omega t term for various values of time over one cycle. So starting from t equal to 0 here, ending up to one full cycle at t equal to capital T, but increasing the time by 1/8 of the cycle every time. So 1/8 of the cycle in terms of phase angle is pi by 4. So we went from 0, omega t went from 0 to pi by 4 to, pi by 2 to 3 pi by 4 to pi, like that, in increments of pi by 4. Okay, so now let's plot these graphs and we'll understand with that how this sort of standing wave pattern progresses.
Sir. Sir, am I audible?
Yes, you are audible, Beta.
Sir, can you please scroll it up? The above part of
Okay.
the system.
Okay, I'll scroll it up. Just give me a moment. This part?
Sir, about it, about.
Acha, above this.
I mean the heading part.
Yeah. Okay.
Yes, sir. Enough.
Okay, done?
1 second.
Yeah.
Done, sir.
Okay. Now this part is clear now.
Yes, sir, that's done.
Okay. So now what we'll do is we'll start plotting these. So it seem like a lengthy task, but it's not going to be too difficult once it's organized. This much should be enough. Okay. So now when we start from t equal to 0, so at t equal to 0, we saw that all the medium particles were at the mean position. We saw that y was equal to 0. Then when we incremented it to 1/8 of the time period, we saw that y was root 2a cos kx type of graph. So if this is, let's say, a, and therefore this is 2a, root 2a somewhere in between the two. So the graph would look something like this, let's say now. So I'm just plotting in one cycle properly, and then the thing repeats itself. I'm going to detail that. Okay. And then next plot, if we see at t by 4, so y becomes 2a cos kx. So we can see that now it has become like this. So you can see how it has changed like this. Okay. Now if we carry that on now, so this is, now we'll see that it comes back to this position, root 2a cos at t equal to 3t by 8. It actually comes back to root 2a cos kx. Then the next plot we take. What's it? So we had t by 8, then t by 4, then 3t by 8, then t by 2. Yes. So again, it's come back to the mean position. Now next, if we add another 1/8 of time, so we come to the time of 5t by 4. Sorry, 5t by 8. So then we see it becomes minus root 2a cos kx. So this graph now goes to this kind of a shape. And then by the time we go to another 1/8 of a cycle, we are at 3t by 4. So y becomes minus 2a cos a. So now it becomes like this. And so on and so forth. So it continues like this. So basically, if we put all this together, we'll see that starting from the mean position at t equal to 0, it eventually comes back to the mean position. But in between, it goes to this kind of position at t equal to t by 8, and then again 3t by 8. Then it goes to the extreme position of having an amplitude of 2a. This is happening at t by 4. Then it's coming to this side. We'll have this at 5t by 8, and then again at 7t by 8. So what we can see from this diagram is that example, in this case, the particles which are located at 0, lambda by 2, lambda, and then further ahead 3 lambda by 2, etc., they are oscillating with an amplitude of 2a. Whereas the particles which are at lambda by 4, 3 lambda by 4, further ahead 5 lambda by 4, etc., they are going to oscillate with 0. I mean, they are not oscillating, they are remaining fixed. So this one, this green colored line was again at t equal to 3t by 4. So you can see that at x equal to 0, x equal to lambda by 2, x equal to lambda, x equal to 3 lambda by 2, and so on and so forth. Multiples of lambda by 2. The amplitude of oscillation is equal to 2a, because cos kx at these terms will become cos of n pi, which is plus minus 1. So the amplitude, which is 2a cos kx's mod, becomes 2a. So this is the maximum possible amplitude. So these are particles with maximum amplitude. So these are called the position of the antinodes. These are the positions of antinodes. In the diagram, we'll represent them with A. So these are the antinodes. So you can see the distance between consecutive antinodes is lambda by 2. So again, I'll minimize this a little, but basically you can see it is just that sequence of snapshot pictures that we had written down earlier in equations. Now we are plotting them in graphs. You can see how the shape of the string is changing in increments of 1/8 of the cycle over one full cycle. Do you want me to zoom in or zoom out? Yes, it must be zoom out, right? Okay. Now,
So just a minute, can you please scroll it up?
scroll it up. Okay. Here?
Done.
Yeah. So these diagrams are clear now with respect to the equation we have written. Now also next sequence of points you can see are the ones where there's no displacement. So they are happening at x equal to lambda by 4, x equal to then 3 lambda by 4, then x equal to 5 lambda by 4. And this sequence will continue as odd multiples of lambda by 4. So what you will see at these odd multiples of lambda by 4 is that cos kx will become cos of odd multiple of pi by 2. So that will become 0. So the amplitudes at these points will be 0. So this is the minimum amplitude points. These are the points which become like fixed points because the amplitude is 0. So these are collectively called the nodes. Yes, these are positions of nodes. You can denote with the symbol L, N. So in the diagram, you can see these positions are the nodes. Like this. So the distance between consecutive nodes is also lambda by 2. And the distance between one node and the next consecutive antinode is lambda by 4. So on any standing wave pattern, you will see that on the x-axis, you have alternate nodes and antinodes equally spaced out. And then the shape of the medium at different times always like this. So anyhow, the distance between one antinode and one consecutive node is lambda by 4. They are spaced out at lambda by 4, whereas two consecutive nodes lambda by 2, two consecutive antinodes again lambda by 2. So they are equally spaced out. At the midpoint between two consecutive nodes, you will find an antinode. At the midpoint of two consecutive antinodes, you will find a node. And the amplitude at any point between a node and an antinode will be anything between 0 and 2a, depending on the value of x. That mod cos kx term determines how much the amplitude will be. Okay, so now that this geometry of
Sir,
yeah,
sir, not copied.
not finished. Okay.
Done,
Okay.
sir. Sir,
Right. So next we'll move on to understand another aspect of standing waves. So we saw standing waves in this way being generated by the superposition of waves traveling in the opposite direction of same frequency and same amplitude. But now standing waves can also be produced by something called resonant modes of vibrations. So standing waves produced in the resonant modes of vibration. For a stretched string now the most important thing of finite length. So we are not talking about a progressive wave. Moving along an infinitely long string, but we are talking about a stretched string of finite length and resonant modes of vibrations created for it because of its geometry and because of its nature in terms of the boundaries. So let's understand this in detail. So the first case of this we will see is a finite length string with both boundaries, okay, a stretched string with both boundaries fixed. So these are our fixed boundaries, a fixed end of the string, which is acting like a fixed boundary. And this is a thread of tension T and linear mass density mu. So if we take a system like this, where a string is stretched between two fixed ends, and we pluck the string or we give it some oscillational energy, then we will see that it vibrates in a particular pattern. Okay. In fact, it has certain possibilities of patterns of vibrations. Only certain allowed patterns are there. And those allowed patterns are called the resonant modes of vibrations. Okay. So the fundamental mode of vibration, you can think of fundamental mode of vibration as the simplest possible mode of vibration that can be generated by just plucking the midpoint. If we pluck exactly the midpoint of the string, we'll see that it will go into a mode of vibration where the midpoint has maximum amplitude of oscillation. So the midpoint of the string acts like a antinode, whereas the two fixed ends, because they are fastened to a rigid wall, they will act like nodes because they will not have any displacement amplitude. So the string will vibrate in a pattern which over time looks like this. See, this is the shape of vibration of the string. So when it is vibrating in this pattern, the length of the string is equal to the consecutive distance between two nodes. So it's lambda by 2. So the frequency of the fundamental mode, it is referred to with f0, okay, or with a subscript of 0. That becomes 1 by 2L square root T by mu. Because we have the relation that B is equal to f lambda, okay, and V here is square root T by mu. And lambda for the fundamental mode becomes 2L because lambda by 2 is equal to L. So from that we have this. So this is the fundamental frequency for the resonant modes. So by fundamental frequency, we mean it is the lowest possible frequency. of vibration for the given string. So a practical way of achieving this particular mode of vibration would be, as I said, to plug the string exactly at the midpoint so that the midpoint of the string has maximum amplitude for displacement. So it forms the antinode. When it vibrates in this pattern, it will form a shape like this. The entire length of the string will look like a loop. Okay, now the next possible mode in which this system can vibrate will be a situation like this, where we have another pair of node and antinode. So it is like the fixed ends are constrained to be nodes. So a standing wave pattern has to always be a pattern such that it accommodates that constraint, that these 2 points have to be nodes. So the simplest situation is if the midpoint is the only other antinode. But now the next possible simplest situation is when the midpoint is also a node and we have 2 other antinodes. So as the string vibrates, it forms a shape like this. So the next possible frequency at which it can vibrate will correspond to this particular shape. And in this shape, so this is called the first overtone mode, because it's the next higher frequency possible after the fundamental. So the first overtone has a frequency F1, which we write. It's the next higher possible frequency after the fundamental. So it's F0. That means the string cannot vibrate at a frequency which is between F0 and F1. If the fundamental frequency of vibration is F0, then the next highest frequency or the next possible frequency at which it can vibrate will be F1, which is the first overtone mode. So in the first overtone mode, you can see that you have lambda by 2 between node and node, and then again lambda by 2 between node and node. So the length of the string becomes equivalent to 2 half wavelengths. The frequency becomes 1 by lambda to square root t by mu. So that becomes 1 by L square root t by mu. So if you compare it with the first formula, this becomes double of the fundamental. So this is the formula for the first overtone mode. It has a frequency which is equal to 2 times the frequency of the fundamental. Now, before you write this down, let's look at another member of this sequence. So second overtone mode. This has a frequency which we denote by the symbol F2. So this is the next higher frequency after the first overtone. Okay. So in this mode, we have the next possible simplest shape for the given string. So we have to include another pair of node and antinode. Okay. So in the first overtone, we had the 2 ends were nodes, and add to that we had one more node at the midpoint. Now what we'll have to do is we'll have to accommodate 2 more nodes, and therefore the system will have 3 antinodes and 4 nodes. So each time a pair of node and antinode gets added to the mix. So the string will vibrate in this sort of a pattern now. So as it vibrates in this sort of a pattern, you can see that the frequency corresponds to the situation where the length of the string is occupied by 3 half wavelengths, or 3 loops, you can say in that sense. So L in this case becomes 3 lambda by 2. So the frequency of this second overtone becomes 3 by 2L square root t by mu, because lambda is 2L by 3 and frequency is 3 by lambda. So if you compare this with the fundamental again, you will see that this is 3 times the fundamental frequency. So this sequence follows now. Okay. This follows as a series as we go from fundamental to higher and higher frequencies. Okay, so now as we look at this sequence further, we can understand that, for example, the third overtone mode, it will have a frequency which will become 4 times the fundamental. Okay, because In this case, the length will be occupied by 4 half wavelengths. So lambda will become L by 2. Okay. So frequency will become 2 by L square root T by mu, which is 4 times. So in general, if we continue this, we'll see that the nth overtone mode has a frequency which is given by n plus 1 f naught, okay, or n plus 1 by 2l. General formula becomes like this: square root T by mu, okay, because so the resonant modes, or what we can also call the modal series of frequencies, so here first overtone is 2 times f naught, second overtone is 3 times f naught, third overtone is 4 times f naught, and like this series continues in general to the nth overtone, where the frequency of the nth overtone is n plus 1 times the fundamental, because the string accommodates between the two rigid boundaries or the two fixed boundaries. In the nth overtone mode, it will accommodate n plus 1 loops. Fundamental mode, it accommodates a single loop. First overtone 2 loops, second overtone 3 loops. So like that, that series continues. Like a natural number series, actually more like a whole number series. Okay, so let's see a quick question or two based on this first.
Sir, just a minute, sir.
So still not finished. Okay, done.
So once again. Done, sir.
Okay. So let's look at an example problem. So a certain thread of tension 40 newtons and linear mass density 1 gram per centimeter is stretched between two fixed points. If the frequency of its seventh overtone mode of vibration is 160 hertz, find the fundamental frequency f naught, the frequencies of third and fourth overtones, then the length of the string, thread or whatever. Okay, and now fourth part, if the tension is reduced to 10 newtons for the same linear mass density and same length, find the new value of the fundamental frequency f naught. Okay, so just try this out, people. We'll discuss. Okay, so I'm just going through your answers. We'll check the values. Yes, Yash, correct answer. Vashisht, correct answer. Very good. Okay, so let's understand this. So first of all, seventh overtone is 160 hertz. So remember that the general formula is that nth overtone is n plus 1 times the fundamental. So seventh overtone will be 8 times the fundamental frequency, which is 160. So fundamental frequency is 20 hertz. That should be the first thing. So naturally, the third overtone will be 80 hertz, and the fourth overtone will be 100 hertz. And the fundamental frequency is given by this formula. So here 20 is equal to 1 by 2L square root of 40 divided by 0.1, because this should be in kg per meter. Always remember this. So 20 is equal to 1 by 2L into square root of 400. So that's 20. So 2L is equal to 1, or L is equal to 50 centimeters. So the length is 50 centimeters. Okay. Now come to this part, the fourth part. Sort that out. Yes, very good. So you can see that you have the relationship of fundamental frequency with respect to tension is like this. So if keeping tension the same, I mean tension different, you keep everything else the same. This will be like in these two cases, okay. So it was 20 hertz when the tension was 40 newtons. Now the tension has become 10 newtons. So the fundamental frequency now will become 10 hertz. In this situation, the new value of fundamental frequency will become 10 hertz. Yes, very good. Tantresh, Tej, and Ansh. Yes, so I will conclude today's session here. What will be the reason for the next lecture being at 6 o'clock? But anyway, and plus some of you are having exams tomorrow also, TP Bhatia people. So we'll pick this up in the next week. We are basically done with transverse waves on a string now. So next week we'll pick up sound. That's it for today's session, people. Wish you all the best and have a nice day.
Bye, sir.